So here for the section, our notes for our section 7.5, which is the logistic growth. So just to know about how populations grow. Population's nature cannot sustain exponential growth for very long. In real life, available food, habitat, living space will eventually restrict how many creatures, animals, people, trees can live in a certain place. So the populations eventually will level off. If we're going farther, we're going to talk about partial fractions and decomposition. So this is essentially undoing a common denominator to break one fraction down into several. So here's how it works. So write the function x minus 13 over this as a sum of rational functions with linear denominators. So what we're going to do, is the first thing that we need to do is to factor our denominator. So let's see here. We'll say it's going to be 2x probably in x, and that's going to be minus 3 and minus 1. So I need to multiply to positive 3, and I need to end up being negative, so I need double negatives. Then what we're going to do is we're going to take this fraction and break it into two other fractions. Each of them has some unknown numerator, but the denominators are factors of the original denominator. Now, to solve this, what we're going to do is we're going to take the whole thing and multiply by the common denominator, which is the factored form of our original denominator. So when I multiply the first fraction by that, everything cancels, which leaves me just the x minus 13. When I multiply the a fraction, the 2x minus 1's cancel, leaving me a times x minus 3. When I multiply the b fraction, the x minus 3's cancel, leaving me the b and the 2x minus 1. So this has to be true. Now, in order to find out what a and b are, we need to essentially eliminate either a or b. So for example, if I make x equal to 3, this equation becomes 3 minus 13 equals a times 3 minus 3 plus b times 2 times 3 minus 1. So that's going to be 0. It's going to go away. So I have negative 10. That's 6 minus 5, so that's 5b. So b is equal to negative 2. So do the same thing. So over here, in order to make this go away, I would use 1/2. What makes 2x minus 1 equal to 0? So 1/2 minus 13 equals a 1/2 minus 3, and the b term's gone. I'm not going to even bother writing it. So let's see here. 1/2 minus 13 is negative 25 halves. That's 26 halves. 1/2 minus 3 is going to be, let's see, it's going to be negative. That's 6 halves, so negative 5 halves a. So a is equal to, positive 5. And then I just go back up to my original pair and plug them back in. So that fraction decomposes as 5 over 2x minus 1 plus negative 2 over x minus 3, which is usually written like this: 5 over 2x minus 1 minus 2 for x minus 3. Now, when you do the split step, what you call a and what you call b don't really matter. You may get your answers in a different order. What you call b, I may call a. So, but the numbers, the answers should come out to be the same. The terms may be in a different order, but you should have the same terms in general. Okay, so example 2. Find 3x to the 4th plus 1 over x squared minus 1. So what we're going to do is we're actually going to decompose. Let's see here. Oh no, we got to break it down first. Do I have to break it down first? Let me think. So I wonder if I can just decompose this right away. Factor that. Gives me that. Yeah. So my numerator has to have a smaller power than my denominator. So I actually need to work out this division. So off to the side here. So I think that was, I lost my little notes, where the degree of p is less than the degree of q. So the degree of the numerator has to be less than the degree of the denominator, so we actually have to work out the division. So 3x squared, or 3x to the fourth plus 1 divided by x squared minus 1. So I would need to multiply by a 3x squared. Actually, we're going to do something plus 0x cubed plus 0x squared plus 0x plus 1. We're going to fill in the missing values here. So 3x squared times negative 1 is negative 3x squared. And then we subtract. So those cancel. I get negative 3x squared plus, no, positive 3x squared because I'm subtracting a negative, plus 0x plus 1. So to turn x squared into 3x squared, I need to multiply by a 3. So that gives me 3x squared, gives me minus 3, draw parentheses, subtract. So those cancel. 1 minus negative 3 is 4. So this divides out as 3x squared plus 3 plus 4 over x squared minus 1. So I'm going to rewrite this, antiderivative of 3x squared plus 3 plus 4 over x squared minus 1 dx. Now, since for an integral you can break it apart, so this is the same thing as the antiderivative of 3x squared dx plus the antiderivative of 3 dx plus the antiderivative of 4 over x squared minus 1 dx. Now, these two are relatively straightforward. This one's going to be tricky. So what I need to do is I need to partial fractions this guy. So 4 over x squared minus 1 becomes 4 over x plus 1, x minus 1. It's going to be something over x plus 1 and something over x minus 1. So common denominator, multiply everything by the x plus 1, x minus 1. So I get 4 equals a times x minus 1 plus b times x plus 1. Just as a shortcut, whatever's not underneath this denominator shows up. So this x plus 1 goes here, there. Now if you have a, b's, and c's, it gets a little bit trickier. So if x is 1, the a goes away, so I get 4 equals 2b, so b is 2. If x is negative 1, the b's go away, so I get 4 equals negative 2a, so a is negative 2. All right, so here we go. So we have the antiderivative of 3x squared dx plus the antiderivative of 3 dx plus the antiderivative of my first fraction, which is negative 2 over x plus 1 dx plus that one. So 2 over x plus 1 dx. So those are my 4 integrals that I have to work out. So let's see here. Let's see, so we need the antiderivative all of this stuff. Okay, so this one, count the exponent up, we get x cubed. The 3 would go away because it multiplied by 1/3. For the 3, that just become 3x. Now there's kind of a shortcut for this when you do these guys. What happens is the numerator becomes a coefficient on a natural log, and you need absolute value bars. So, and this one's going to become plus 2 ln. One of these is minus 1. That should be minus 1 down there. And then slap your plus c on the end. All right, so we've got these log terms can actually be combined because they're being subtracted. So actually, we'll look at it this way. So x cubed plus 3x. We're going to actually factor a 2 out front. That's going to give us ln x minus 1. That's this term, minus ln x minus 1. Since you're subtracting the logs, what you are actually doing is dividing them. So 2 ln x minus 1 over, I keep messing it up. That one should be plus 1. X minus 1 over x plus 1 plus c. Or you can make this just single absolute value bars because the whole thing has to be positive. So that is your final answer. All right, last one, find the general solution, not last one, next one, to this. So we can factor this. If you notice, the bottom has a degree of 3, x squared and x, so it is already, we can already do partial fractions. So 6x squared minus 8x minus 4. That first one's a difference of squares. It's x plus 2, x minus 2, x minus 1. So this is going to be equal to something over x plus 2 plus something else over x minus 2 plus something else over x minus 1. So when I get rid of the denominators, this side is always just what the original numerator was. The a is going to be stuck with the x minus 2 and the x minus 1. The b will have the x plus 2 and the x minus 1. And the c will have the x plus 2 and the x minus 2. The other denominators, essentially. Each numerator gets the other denominators. Okay, so let's see here. So we'll do this a little bit differently. We'll look up here. So we're going to use negative 2, positive 2, and 1. So if x is equal to negative 2, so we'll go over here. We'll just do it right here. So if x is equal to negative 2, we'll figure out what this guy is. So that's 6 times 4 minus 8 times negative 2 minus 4. So that's 36 is equal to, so when x is negative 2, everything except for the a term is going to go away. So that's negative 4. So negative 2 minus 2 is negative 4. This is negative 3. So negative 4 times negative 3 is 12. So a is 3. So essentially a shortcut to figure out which coefficient it is, or so what the numerator is, you use what makes the bottom 0. So when x is 2, that's going to tell me what the b value is, because a and c are going to go away. They have the x minus 2's. So when x is 2, this becomes 24 minus 16 minus 4, which is just 4, equals, so the b is the only one I have to worry about, so 4 times 1, so it's 4b, so b is equal to 1. And lastly for c, I'm going to use 1, so when this is 1, this is 6 minus 8 minus 4, that's 6 minus 12, so that's negative 6. This is the only one that matters, 2 times negative 2 is negative 4, so c is equal to 3/2. Okay, I think I'm off somewhere. That's 3 times negative 1. So that's negative 3, which means this is just 2. Okay, so building our fractions back, we have 3 over x plus 2, plus 1 over x minus 2, plus 2 over x minus 1. And we're doing the antiderivatives of each of them. Numerators become coefficients, bottoms become natural logs. So absolute value of x minus 2 plus the natural log of the absolute value of x minus 2 plus 2 natural log of x minus 1. And then just slap your plus c on the end. So the thing that happens is that these numerators are actually exponents. They're all being added, so I'm going to multiply all this together. So it's the natural log of the absolute value of x plus 2 cubed times the absolute value of x minus 2 times the absolute value of x minus 1 squared plus c. So that's my answer. Okay, differential equation. So dp dt is kp and minus p. So the growth rate of population p of bears and newly established preserve is modeled by the differential equation blah, 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 whereas measured in years. What is the carrying capacity? So in that formula, p is the current population, k is some constant, and m is what's referred to as the carrying capacity. So let's see here. Bears here? Okay. So the carrying capacity for the bears. That is the m value, so that is 100 bears. What is the bear population when the population is growing the fastest? So that occurs at half of the max population. So p is equal to 50. What is the rate of change of the population when it's growing the fastest? So let's see here. have enough info? Oh, yeah, there's my formula. So P goes in for that, so 0.008 times 50 times 100 minus 50, so 0.008 times 50 is 20. So dp dt is equal to 20. So when the population is growing the fastest, there's 20 new bears that year. Okay, example 5. In 1985 and 1987, Michigan Department airlifted 61 moose from Algonquin Park, Ontario to Marquette County in the Upper Peninsula. It was originally hoped the population P would reach carrying capacity in about 25 years with a growth rate of blah, blah, blah. What is a carrying capacity? That's the M value, 1,000. The calculator generates slope field. I'm not worried about the slope field. So solve the differential equation with the initial conditions P0 equals 61. All right, so I was checking my work and I noticed I made a mistake on this example, so I'm going to delete it and replace it with this one. That's why it looks a little bit different. So example 5 gives you this equation. It's modeling some moose population and asks about the carrying capacity, generating a slope field, and then solve the differential equation and show that it confirms the slope field. So I'm not really worried about the first two parts. They'll be the old version, but the work for the last part, where we have to solve the differential, I do want to work out. So the first thing we have to do, because that's where my mistake was, is separate our variables. So everything with p's needs to come left. Everything with this dt needs to come to the right. So I'm actually only going to move the p and the 1,000 minus p over. So it becomes 1 over p times 1,000 minus p dp, and we're going to leave the 0.0003 over here and bring the dt across. So separate your variables. So to get rid of the derivatives, we need to take the antiderivative both sides. Now this we have to do partial fractions on. So this is something over p plus something over 1,000 minus p. So I got that equation. So I need to work out what these values of p are. So they have to equal 1. So if you remember the trick, it's the original numerator is equal to a, in this case, times the other denominator, plus b times its other denominator. So if I make p equal to 0, it's going to give me the value for a. So 1 is equal to 1,000 a. So a is 0.121, 1,000th, if you want the fraction version. For b, p has to be 1,000, so that's going to make a go away, and I have 1,000 b, so b is also 0.001. So this becomes the antiderivative 0.001 over p plus 0.001 over 1,000 minus p dp equals the antiderivative 0.123 dt. All right, so I'm going to do a little bit an extra step to make my math a little bit easier. This is 1/1000th, and I've got these small decimals, so I'm actually going to take everybody times 1,000 to make these numbers a little bit easier. So it just becomes 1 over p, 1 over 1,000 minus p, and this becomes 0.03 dt. So just to make my calculations, not 0.03, I think I have an extra 0 in there, 0.3. There's an extra 0 somewhere. Anyway, 0.3 is what it comes out to be. 1, 2, 3, move it 3 places. Okay. So remember the trick for this, the numerator becomes the coefficient, the bottom is a natural log. So this is the natural log of the absolute value of p. This over here, you have to be careful, since it's a negative p, it's actually going to be minus the natural log. And over here, we're going to have 0.3 t, because we just slapped the t on the end of it. So let's see here. What can we do next? So I'm going to multiply, oh, sorry, forgot a plus C. Bloop, bloop. These absolute value bars aren't necessary, but I'm going to multiply everything by -1 because I'm going to reverse the order. It's going to make my math easier in the end. So this is going to become the natural log of 1000 minus P minus the natural log of P equals -0.3T minus C. So these are being subtracted, so I can combine them into a single log term. So 1000 minus P over P equals -0.3T minus C. So you get rid of the ln, everything becomes an exponent on an e. So I get 1000 minus P over P equals, let's see here. How would I want to write this? E to the -0.3T minus C. So looks like this. So what else do we know? Now we can break this guy apart. I'm actually going to simplify this. This is actually 1000 over P minus 1 equals E to the -0.3T times E to the negative C. Okay, I can bring the 1 across. So 1000 over P is equal to 1 plus E to the -0.3T E to the negative C. So now I can use my initial conditions. So it tells me in the problem that the initial conditions, let me make sure I got the numbers right, the population is 61 to start with. So T is 0, P is 61. So let's see here. So 61, this becomes 1 plus, so this becomes just 1 e to the negative c. So let's see here. We're actually going to leave it in terms of e to the negative c here. So 1000 divided by 61 is that minus 1. So we get 15.39 equals e to the negative c. Okay, and then we're going to come all the way back up to this line. The reason that I didn't solve for c is I'm just going to have to plug it in back up here and reevaluate, so I might as well just leave it as e to the negative c. So this equation becomes 1000 over p equals 1 plus 15.39 e to the negative 0.3t. Now, this p is on the bottom, I need on the top, so I need to reciprocal both sides, or technically raise everything to the negative first power. So this becomes p over 1000 equals 1 over. So I just did a reciprocal on both sides. You can do that if you have a single fraction, or treat that as a single fraction. Now to get p by itself, I have to multiply both sides by 1000. So it cancels over here, so I just get p equals, this 1000 only multiplies into the numerator, so 1000 over 1 plus 15.39 e to the negative 0.3 t. So that is the population equation. Well, technically it's p of t, but same thing. We'll model the moose population given in the problem. That's the end of this example. All right, so this is a much cleaner version. General solution looks like this. MK, where A is the growth constant, carrying capacity. Logistic growth are positive constants. Okay, so example 6. The growth of the population of Aurora, Colorado for the years between 1950 and 2003 was roughly logistic, satisfying this equation. Model the growth of the logistic function using the initial condition P0 equals 12,800. Okay, so let's see here. Oh dear, where's that notes? Shouldn't have slid it off to the side. Okay, so let's see. What's the best bet to do this? So we need to factor out this garbage decimal first. So 3.125 times 10 to the negative 7th times P times, and if we divide that out, this actually comes out to be 32,000 minus P. So now if you look at our formula, that value is our K, that value is our M. So we can build our equation. So P equals M over 1 plus A, which I don't know yet. E to the, let's see here. What goes up in that exponent? MK, so M times K. So that's actually that value there, negative 0.1 T. This is negative KT. All right, so when T is 0, the population is 1280, so this formula becomes, 12,800 equals 320,000 over 1 plus, now if T is 0, this becomes e to the 0th, which is 1, so it's just 1 plus A. So doing some cross products, 12,800 plus 12,800A equals 320,000. Subtract that across, divide by that. So let's see here. Let's see here. So 32, 120, 1, 2, 3. That's too many zeros. 1, 2, 3 minus 20,100 divided by 128. 1, 2. So A is 24. So the equation is P equals 321,234 over 1 plus 24 e to the negative 0.1 t. And that is the end of that section.